So I'm going to talk about the materials, and this is the outline. So I'm going to talk about the role of materials on the semiconductor roadmap. I know, looking at the list of who's attending the course, that most of you are EE. So I'm not going to bore you with a lot of material science, but I think there are a few key concepts that are needed, and I'll illustrate them, those concepts, in the processes that I'll be talking about, and they're very, very relevant. So I'll be talking about them applied to new devices and processes. And then I want to talk about the advanced, since materials play a major role. I work for this company called Intermolecular that builds this advanced materials R&D platform to help in the innovation process. And then last of all, I wanted to point out that it's interesting that we introduce a new material for a very specific type of device, and we'll be talking about the transition metal oxides, and then we find that we can use them in a wide variety of other, and so a lot of the learning that takes place on the basic fundamentals can be reused again in some other device. So having a good, solid, fundamental understanding of materials is incredibly useful. So we'll talk about the device interconnect evolution, and then I'll talk about what is the role of materials. So you may have seen this as part of some previous lectures. What was the evolution of the device starting back at 2003, and here we, even from 2003 to 2005, if you look back at the industry even before this, so there's if I look back at the 3 decades, the first when I came into the industry, it was all about materials, and there was a lot of fundamental work done at materials in many places, in TI, in Fairchild, etc. But they were all around the silicon and silicon dioxide. And Stanford, by the way, was also one of the pioneers in understanding a lot of the properties that were needed, and they developed the process simulator called Supreme that I used quite a bit. And then, strangely enough, later on, when I, as Krishna pointed out, I was running the TCAD group in Synopsys, and I'm back again, not only using it, but actively trying to sell it to a lot of the customers. But there was a lot of fundamental understanding done on silicon and silicon dioxide. And then in between, the next decade was all about scaling, and you've heard from one of the lecturers, I believe from Intel, about the whole lithography roadmap. And lithography still is a major part of the evolutionary process of devices. Scaling, lateral scaling is still a big issue, and there's a lot of money and effort that goes into it. But starting really from the 90 nanometers, especially in the front end, there's been a lot of again, a resurgence of interest in materials. So you have silicon germanium strained silicon being used in order to improve the mobility. In 65, there's further improvements using the strained silicon, both on the P and the N channel. But the gates primarily remain silicon and silicon dioxide and silicon. And then in 45, Intel introduced what they call the gate last high-K metal gate. This was like a really amazing challenge, and I think it was a major accomplishment by the industry to replace polysilicon, silicon dioxide, which had lasted for like decades, right? That was eventually replaced, and there was a lot of challenges associated with introducing these new materials. Then the second generation, again, there was further improvements on the gate last high-K metal gate, and right now we are going from planar to 3D. Again, you must have gone through that in some of the previous lectures. This is what Intel calls a tri-gate. It was introduced initially as a FinFET by Dr. Hu, not the guy with the TARDIS, but HU, not WHO. And I believe one of Krishna's students, Sujay, is that right? Yeah. So they introduced the FinFETs, and Intel has been, like in most of the process areas, been a pioneer in introducing it into large-scale production. And with that, there's come a whole set of challenges, because the high-K metal gate has also got to be integrated together with these, what we call the fins. In the metallization side, usually most of the materials work, and so I got a big start also by developing quite a few generations of back-end metallization. And we started with aluminum and silicon dioxide, but we went through several generations where we introduced alloys and barrier metals. And for example, at the 180 nanometer, you had the aluminum and clad aluminum and tungsten vias, and there was a lot of challenges associated with the materials, both the metals and the oxide, and a lot of this was the traditional type of materials issues that a typical material scientist would have to deal with, and with this involved you know, a lot of the issues with mechanical issues, but also some incredibly subtle what I would call chemical / electrical issues. And then the biggest change in the metallization was the introduction of the copper damascene by IBM, and that allowed the further what I would say, the further improvement of the whole interconnect stack, in allowing almost like 9 levels of metal. The evolution since 90 nanometers looks, I would say, it's not so much of a revolution as a steady evolution. The feature sizes have decreased. There have been further improvements in the alignment, and this is the latest 22 nanometer process from Intel, where they've used a set of processing and integration innovations to not only to shrink the size of the lines, but also to improve the alignment of one level to the other, so they actually can shrink. So the whole idea, you know, in both the device as well as the interconnect side is to shrink, as you've seen, but it's also to improve, have a corresponding improvement in performance at the same time. So both are necessary, the scaling as well as the improvement in performance. And so part of this is also when what happened is at the 250 nanometer node is that the designers had to integrate both the devices and the interconnects and think about the whole design flow part of it, both from a timing point of view and from a lot of other considerations like voltage drops, etc. So now if we go back again in time and we start looking at what has happened, if you look at the 1980s, there were only a few elements in the periodic table that were being used, and typically, as I said, the main materials being used were silicon dioxide, and aluminum, but you had all the dopants. So these are the few elements that were existing in the, but come the 1990s, as I said, we started looking at titanium for silicides, tungsten silicide, tantalum. So, you know, a few more, but in the main, the 1990s were known as the decade where we were looking more at the lithography. And then from the 2000s, as a result of all the introduction of all these new innovations in the device level and also in the back-end interconnect, the number of elements that we had to, that were being investigated exploded dramatically. So it's almost like we got to look at everything in the periodic table except the radioactive elements. I guess the people who did look at the radioactive elements didn't survive through, but that's I should probably say that. But so this is where we are today. And you know, as we've talked about, we're also going from a planar type of devices to 3D devices. So the trend now is all about new materials and device architectures. And if you look at what has been driving, as I said, it's not only about scaling, but about improving performance. We want more and more drive out from the transistors. You want to be able to have the interconnects handle larger and larger frequencies. And if you look at what has been, you know, typically in the past, the performance automatically came as a result of the scaling. And I think some of you, you would have probably heard about the scaling introduced by Dennard, that as you scale the lateral dimensions, if you scale the vertical dimensions and you scale the voltages also in proportionally, you automatically get a lot of improvement from a performance point of view. But starting from the 2000s, if you look at what percentage of the performance is from scaling and what percentage is from materials and device architecture, is becoming a larger and larger fraction, such that at, at 28 nanometers, it is a big aspect of it. So once again, I just want to emphasize, scaling is extremely important. That drives what you call Moore's law, but materials is what is allowing the scaling to continue by providing the enhanced performance that is needed. And so it's good, so again, it seems like in the 1990s and early 2000s, even Stanford seems to have lost its way. There was less materials and less device work done. And it's nice to see now again that the Stanford is spending a lot more time back again on materials and devices. And that, devices and materials are not dead. These are an integral part of the next generation of devices and of progress. So that's so that is going to be, the theme of my talk is that the future is materials and device architecture. We need new materials. It's, we need, as I showed, we are using almost every element that we can possibly think about. We're using compounds, alloys, to drive the increased functionality that we need. We need to look at new structures, looking at every single type of thin film stacks. It's quite amazing that something as simple as 3 or 4 layers of different types of compounds can give just a wide variety, wide range of properties. And then we're also looking at nanostructures, carbon nanotubes, 2D materials such as like graphene, molyselenide. There's things like topological insulators. All sorts of new 2D materials are coming into the forefront. We're looking at nanowires, and then there's also on the device front, people are looking back again at tunneling devices. So all of a sudden, there's this big investigation of all the new materials, and we're also then as a result of that looking at novel deposition and processing capabilities in order to take advantage of all of this. And the most important thing is to control the electronic property manipulation of the atomic structure in bulk and interfaces. And it's again, it's sort of interesting that the computation capabilities that have been brought about by the semiconductor revolution is also driving our ability to actually look at and use simulations to look at how a lot of the properties of the materials can be changed by just moving atoms around. And so, for example, out here you have Blanca doing a lot of work. I have a person here who's in the audience, Sergey, who's also, we are doing a lot of work also on ab initio, where we try to understand what's happening both to the mechanical property, I mean not just electrical properties, but various other properties. And it's amazing that just moving an atom just by a lattice distance or less, you can fundamentally change the characteristics of a device. But that's the level of control that we are trying to get out with the level of material processing. And that means also, we have to characterize the films at the atomic level. So there's some amazing pieces of equipment that are being developed. I mean, the TEM that are being developed these days are getting to a point where I just saw one where they could look at the individual atoms on a particle and even look at the catalytic activity caused by the movement of an atom on a surface. Plus, of course, all the AFM and scanning conductance microfilm. So in addition, above all, you need the platforms, methodology, knowledge to accelerate the learning cycle of materials. So I'm going to be talking about some of the problems, and at the end, I'm going to talk about what the company I work for does. We have, as part of our business, is to take advantage of this whole sea of change that is happening in the materials world. So now, I'm going to talk about some key material science concepts. And as I said, I know most of you are not material science, but maybe EE, but I'm just going to keep it relatively simple because these are two key concepts that I need to get. One is the question of transformations and one is of kinetics. And the second thing is a lot of the properties of films are decided by defects. And at least you have to have some concept of what defects do. So, so in the background, so there are really two things I want you to think about, right? Whenever we process materials, and in our case, we are talking about depositions, annealing, reactions between, we need to know what is driving the transformation and what direction is the transformation, right? That's decided by thermodynamics. But just because something can be changed, right, doesn't necessarily mean it'll happen fast enough. And we are really interested in how fast these occur. So we are interested about kinetics. So anytime I look at a problem, a materials problem, I ask, is it thermodynamically, is it possible thermodynamically? And secondly, even if it's possible thermodynamically, can I do it in fast enough that it's useful, right? I mean, if something is going to take a million years, I mean, in fact, the whole history of materials around, if you look at the Earth, it's all about eventually everything goes into thermodynamic equilibrium because they've been around long enough. And typically, as the human beings have come and reversed that process, we have extracted all the metals from the oxides, which are the most thermodynamically stable form in an oxygen environment, and converted into metastable. So just imagine everything that you see in principle is probably highly metastable. But fortunately, the lifetime of these, or unfortunately, because we're talking about sometimes when we talk about recycling, we only want them to last as long as they're useful. But a lot of times they stick around for a long time. So what thermodynamics tells us is that a reaction should happen if the products are more stable than the reactants, right? And we'll talk about free energy. So the reaction will have a negative free energy. So it's sort of like, okay, it's like the concept of potential energy. If something has a very high potential energy, it will be converted into kinetic energy given the right pathway. The kinetics, on the other hand, tells us how fast the reaction will go, though it doesn't tell us anything about the final state once it gets there. So, again, thermodynamic kinetics. So, and as I said, some changes or transformation are thermodynamically favorable, but kinetically unfavorable. So you could have metastability. So just because something can happen, so you can think of it this way, that thermodynamics says that something is possible or probable, but it doesn't tell us where it's possible, and possible is defined in terms of a finite, happening in a finite time. So kinetics tells us whether it's finite. So the things which you don't have to remember all this, but just remember there's this term in thermodynamics called the free energy G, which is the H, which is sort of like an energy function. It captures the internal energy of all the components, plus there's an extra term from the PV term, and the free energy includes the entropy, which is given by this. But all you really need to know is that the reason we talk about the Gibbs free energy is that it is an idea of the useful work. So if there is a net change in the Gibbs free energy in any process, that it's negative, then it's going to happen. So again, most of you have done elementary mechanics, right? And it's sort of like, as I said, it's like the potential energy term. If something has a high potential energy, it means in principle you can extract energy out from it and convert it into kinetic energy. So it is important to understand that, and especially for a lot of the materials that we've talked about, we have to look, and I'll give examples of because without understanding that, the concept of free energy is sometimes difficult to understand why certain things happen. And if you have a large number of components, you can actually define a Gibbs free energy, which is the per component, per unit item of component, and that's the usually called the chemical potential, and it's given by this term. Now the interesting thing is that we add up all the effective chemical potentials of each of the components, and if you had, say, a system, right, with multiple components, but suppose that in the transformation only one of the components free energy changed. Then we only need to think about that and look at what happens to that, because the rest, the free energy of all the other ones are constant, right? So I'll give examples of that, because that's the simplest case, because then in spite of having all these large number of atoms and things happening, you just focus on one and you look at what happens energetically to that particular atom or element or whatever. The other thing is, if you have multiple components, and if their energy is changing, each one of them is changing, then it's a lot more complicated, because you can have a situation where the energy of one will increase and the energy of another one will decrease, and if the decrease of one is larger than the increase of the other, then it can happen, then that can happen. And so you get these scenarios where it looks like, why is something going against what we call the concentration gradient, right? I mean, you normally think about diffusion, which is usually a atom going from a high concentration region to a low concentration region. You can have a situation where it seems to do the opposite, and the reason it does the opposite because there's either some force or there's some other change that is taking place that compensates for that supposedly increase in energy of that particular component. So it becomes really complicated. So as we try to make sure that we try to keep things simple and try to see if we can represent everything by just a single component. And the corollary of that sometimes is, and I'll give an example, is people, when we look at some of the transition metal oxides, we'll be talking about defects, and if there are multiple types of defects, it's really difficult to figure out what can happen under different circumstances. So to keep things simple, you may make a selection of a material where there's only one component that is moving around and causing things, if it meets your requirements.